നമസ്കാരം. നമുക്കിന്ന് വളരെ പ്രത്യേകതയുള്ള ഒരു അതിഥിയാണ് ഇവിടെയുള്ളത്, നമ്മുടെ കൂടെയുള്ളത്. പ്രശസ്ത ജ്യോതിശാസ്ത്രജ്ഞയും ജനീവ സർവകലാശാലയിലെ തിയററ്റിക്കൽ ഫിസിക്സ് ഡിപ്പാർട്ട്മെൻറ്റിലെ ഗവേഷകയുമായ ഡോക്ടർ ഹംസ പത്മനാഭൻ. So very welcome. Actually, I would say welcome back to Kerala.
Thank
This
you
is your
very
place.
much.
Yeah.
Always a pleasure to be here.
So I just wanted to introduce you to Victor's channel. So basically, what you do?
I am a cosmologist at the University of Geneva. Like you said, I'm also a theoretical astrophysicist. So these are big words, so I'll say something about what they mean. So I study the evolution of our universe.
Okay.
So we live in a galaxy. Our galaxy is called the Milky Way. So many of people know that here. And just like our galaxy, there are large number of galaxies in our universe. And it is very interesting to know how these galaxies formed, especially what were the first galaxies in our universe. So this is a very exciting time in our universe called cosmic dawn.
All right.
That means when the first light came in our universe. And today we are able to study this in great detail with the help of our big telescopes on our Earth. And you may have heard there are some telescopes in radio wavelengths, like we have radios which we use to hear news and things like that. There are big telescopes which operates in those same frequencies, and they can get a lot of information about the first stars, first galaxies. That's what I study.
That's wonderful. So basically, the kids might be interested in knowing your childhood and how did you reach this domain and what exactly and how is your timeline to reach what you're doing now. So can you explain me, like, how was your childhood and then how did you got into this domain?
Okay. Yeah, I think everyone here has heard interviews of my dad, Professor Thanu Padmanabhan. He was a cosmologist and astrophysicist, and also I grew up in the atmosphere of IUCAA, the Inter-University Center for Astronomy and Astrophysics. It's a lovely center in Pune, which focuses on cutting-edge research in many of the theoretical fields and observational fields in astrophysics. So that was a big, motivator to get into this field. And roughly the trajectory goes like you do your PhD, which is what I did in IUCAA after following your master's degree, and then I was offered a Tamala postdoctoral fellowship, which is given by Switzerland, to take up at the ETH, which is the Swiss Federal Institute of Technology in Zurich, in Switzerland, which I spent 3 years. And after that, I was in Canada. I was offered a 3-year fellowship there at the Canadian Institute for Theoretical Astrophysics. Again, it's a center, just like IUCAA is a center inside the University of Toronto. So it was in Toronto. And even though that was 3 years, I came back after 1.5 years to my current position, where I have an independent grant to conduct my own research project in this field. Actually, it's about the first stars and first galaxies at the University of Geneva. So that's where I am currently.
All right, great. That's a kind of a very impressive profile. So how was your kind of school days? And of course, you are exposed to such a great physicist. But how did your science? I mean, what do you learn? I mean, your science studies in your school helped you, in forming kind of an idea about what you're doing now.
So one thing which I think is very interesting, important for people as well as students who have also asked, is that what are the main subjects which are, noteworthy to get into this field, and what are the subjects that we can study in school itself. One of the things which was a big, plus point, which I really benefited, is that I was very interested in mathematics at a very early age, right from my school days. And I'm sure there are several such initiatives. In Pune, there is one called Bhaskaracharya Pratisthana.
All right.
So this is a advanced mathematics course conducted for school students.
Oh, okay.
Right from the 8th standard to 9th, 10th usually. And some go beyond that also. So this Bhaskaracharya Pratisthana introduced us, they told us, especially as school students, you don't have to confine yourself to the mathematics textbook.
Okay.
You can go and read more, and they taught us a few small concepts in very advanced areas of mathematics for this age. I mean, so it was fun for us because it was taught like a game. Number theory,
Yep.
combinatorics, concepts in geometry which go beyond our classical school curriculum,
yeah.
like the Sivas theorem, many riders, many of those. And that really helped many of us to see all of this learning as a game.
Okay.
So this was such a logical subject, mathematics is, and we were taught in a way which really developed our process of thinking, not just understanding the subject, we learnt a way of thinking. Most importantly, and this is an advice my dad has given to me, so I would like to share it, is that one should, at a very young age, he told me, and this is what he said is important, learn how to learn.
Exactly.
That is really, I would say, the main thing right from school days, that given a bunch of books, now, you know, it's not only books, we
Yes.
have online
All the
resources,
Yes.
lectures, courses. Learn how to learn from them. Then it will help in immeasurable ways.
So be thorough about the basics.
Extremely. One thing which I really want to stress and emphasize in astrophysics is that, you know, astrophysics is very fascinating. There is a lot of glamour associated with it, and I understand the reason for it because, you know, you look at all these beautiful, like I said, first stars is you're looking at this James Webb Space Telescope. I see tremendous interest among the students here, little kids, everybody is interested in. One thing which I would say is, yes, it's very enjoyable, but never compromise on the basic physics up to MSc theoretical physics courses.
Yep.
Those are going to be the foundation, which are like really the stepping stones on which you build the theories of astrophysics.
Yes.
And doing projects in astronomy is something everyone loves to do, but I would just caution that get the fundamentals first and then go ahead, because the astronomy which you need to do a career in astrophysics, you can pick it up in maximum 1 year. You
Okay.
don't, once your physics basics are completely pakka, then there is no, you know, no difficulty in learning the astronomical concepts.
Yes. Basically, when talking about cosmology, so it was like when I was doing my research work with the Sloan Digital Sky Survey. So I was asking my professor what exactly we are looking at, and what he said is, we don't know.
Yeah.
So it's kind of, we are actually looking at the unknown.
Yes.
Or we are searching for the unknown. So that fascinating that studies are. How do you manage? Like, how do you literally search, doing the search for this unknown?
Okay, so there are probably the way most of the people think of this unknown is that there are these extremely huge two elephants in the room in cosmology. And one is called dark matter, one is called dark energy. I'm sure most of the people will be aware. According to the best model we have to describe our universe, this dark matter and dark energy are required to form components of the universe at the level of 95%.
All right.
And only 5% is in what we here, you know, see
Visible.
and are made up of the visible, the atoms, the kind of things, not even visible, even invisible, the atoms, the kind of things we know of are only 5%.
Yes.
And out of that, only less than 10% is visible actually.
Yes.
So 10% of 5%. It's a very small number in stars.
Exactly.
So, of course, that's a very humbling thing for us, but at the same time, it's a challenge. So, this unknown really manifests itself in two ways. First is that you have these kind of observations which are there, like some things called rotation curves, gravitational lensing. There are some things which you can see, which you can't explain if you didn't have dark matter. Now, dark matter is like matter, but which doesn't interact with light. So it can't be seen. You can't, have scattering and so on, which you see in the sky. You can't have it like behaving like normal matter. However, this matter is very important. It forms a huge, like 25% is or more is made of dark matter.
Okay.
The other one is, so the only thing is, in this dark matter, you haven't seen it in the lab, and that is a challenge for cosmology, because by now we have done 40 years of experimentation.
Exactly.
We still haven't seen this in the lab. That is a bit, one of the things people are now thinking about is whether this is now part of some, kind of extended models of physics are able to accommodate this particle.
Yeah.
And trying to see whether that would be able to inform searches for dark matter in the lab. So that is one big thing, unknown. The other unknown is called the so-called cosmological constant, or dark energy, people like to call it. Most people are convinced that this dark energy is like a component to the universe which behaves like a fluid having negative pressure. Now, there is no fluid with negative pressure, etc. This is just in terms of equations. If you write down, this dark energy behaves as if it's a fluid with negative pressure. And it is this dark energy which leads to the accelerated expansion of our universe today. So it's very intriguing. As we know, the universe is expanding. That's shown by observations. Not just expanding, its expansion is speeding with
accelerating.
Time. That is why we have these unknowns. So we measure them by, we only have our small 5% to understand the rest. So we actually have used surveys of this 5% in different, actually in different colors, you should say, because they are different frequencies. You have radio surveys, you have the optical, the visible, you have gravitational waves. Most people have heard of LIGO, to understand this small amount, which will in turn help us, which has helped us a lot to understand what could be the other two.
Yeah. So it's a bit theoretical. What would be, or what are the possible candidates for this dark matter?
So previously people were very interested to have one candidate called as WIMP. Now WIMP is called weakly interacting massive particle, but this WIMP is kind of phasing out right now because we haven't seen the evidence of supersymmetry. There's a phenomenon which is there, and mostly it would have led to a connection to WIMPs being a likely dark matter candidate. But now there is a very interesting candidate which is known as Axion. Axion shows up in many extensions to our standard picture, and it helps us to solve a lot of problems. In fact, the name Axion comes from a US detergent soap. So in order to clean up a lot of problems, this particle has been introduced, and it has good properties which seems to make it a very promising candidate for dark matter. So I would say right now Axion is one of the leading candidates.
Okay, all right. So it's another interesting question that might arise. You cannot see it, you cannot feel it, you cannot detect. I mean, it's very hard to detect, but it is there.
Is there?
This is the idea. Then how you are going to confirm its presence? So, I mean, the tools you are using or the methods you are using. Can you explain?
This is for you're talking about both dark matter and dark energy.
The unseen or the
So dark matter, it's actually a little easier than dark energy.
Yes.
So for dark matter, what people have done is you have these galaxy surveys. So many people here also know there is something called Square Kilometre Array, which is the biggest radio telescope being set up in South Africa and in Australia. It's an international initiative. Several countries are part of it or close to part of it. India, Canada, Switzerland, many countries are there. And this initiative is going to survey large volumes of the sky in radio frequencies. It's going to get hydrogen from the early times, like this cosmic dawn, right until the present time of the universe. And it's going to understand how galaxies formed, like our own galaxy.
Yep.
Now, this kind of initiative, when you have also other initiatives like similar initiative in other frequencies. For example, in the optical, you have big surveys. One is called Dark Energy Spectroscopic Instrument, DAISY,
DAISY.
which is like a galaxy survey. So, both these kind of surveys, you map the normal matter essentially, and you ask how does this normal matter and dark matter, what kind of connection between normal matter and dark matter is warranted by the observation. So,
Okay.
in this context, some of the work which I and collaborators have been doing is to do what is known as a halo modeling. Now,
Okay.
what is a halo model? Halo really is kind of the structure onto which the dark matter collapses.
Oh, okay.
So, at the very early time, so we know this from simulations to very good precision, because dark matter is easy to simulate. There is not much chemistry, there is nothing, it doesn't interact
Yes.
with.
Yes.
So, we take this dark matter just forms into clumps called as halos.
Yes.
Inside the halos, we know that the atoms just collapse and form stars, they form galaxies.
Yes.
So, if we can pin down very well the connection between the atoms and the dark matter, then using the maps of the atoms, we can understand how the dark matter was distributed.
Okay.
That is one of the key ways in which the square kilometer array will help us to understand whether the universe, for example, is populated by axion dark matter, according to a study which a student along with us did a project on. So, this means that you take these maps and you look at how the maps will change if you had different axion particles
Yeah.
in the dark matter, and you find that the square kilometer array can differentiate between the two, between the several. So, that is very exciting. It will tell us something about fundamental physics.
Yeah. So it's like you have to test this theory, or I mean, this results almost everywhere in the universe, right?
Yes.
So it might take long time, right? So,
Exactly. So, something now again I'll give the example of square kilometer array because it is the biggest initiative.
Yeah.
There is something called intensity mapping which comes to our aid in this
okay.
question.
Okay.
Intensity mapping, you can understand from the name, it is like you take a region of the sky and you just make a map of all the emission with very poor resolution.
Okay.
Resolution, people know there's just fineness in distinguishing.
Yes,
So, you don't want to be fine. You be, a little coarse.
Kind of a vague.
Yeah, little low res, no HD. So, you do a non-HD picture of the universe. That is good because it helps you do many things very cheaply and very, quickly. So, this intensity mapping in hydrogen, in neutral hydrogen, is something which the square kilometer array will use.
Okay.
And not just hydrogen, you can do intensity mapping in other species.
Okay.
We recently released the early science of a survey called CO Mapping Array Pathfinder, COMAP, which does an intensity mapping with carbon monoxide. Carbon monoxide is a very nice, it's not very good here on Earth, but it is a very good tracer of stars in the sky,
Right.
in the galaxies. So, therefore, this intensity mapping, you can actually process large volumes of the universe because you take different frequencies, you can do a 3D, understanding of the universe
Yes.
in a short while.
Okay.
And even with that, let me say that there is a word called exabytes,
Yes.
which is 5 exabytes is like it's a unit of information, you have terabyte to petabyte. Now here you have exabyte.
Yes.
This exabyte means 5 exabytes is all the words ever spoken by all human beings from the time the earth was born.
Okay.
This square kilometer array will process 11 exabytes every single day.
Okay.
So, it's huge amount of information.
Data.
It will refine our theoretical, our technology of, understanding this to a great degree. It will really revolutionize the industry.
Okay. So that's a kind of a promising project.
Very much. It's both for the science, and these kind of things are being used, the cutting edge technology is being used to, understand this data, because 11 exabytes a day is unprecedented.
Yeah. So when you are talking about that revolutionizing science, I think there is always a question like, how theoretical physics is helping us. You know, so as you said, this is basically a theoretical physics experiment, but the technology you are developing. So can you get into that domains, like how this theoretical physics or any kind of science discipline, the basic research, is helping us in going forward?
Yeah. So I will appeal to one of the absolutely philosophical and abstract reasons first, and then I will give a more practical.
Yep.
As we have seen so many times in Kerala itself and various other places, the patronage of, the hallmark of a civilized country is that it supports this quest for knowledge in an end in itself.
Yes.
It is something which makes us more civilized.
Exactly.
That is, it is something which the biggest questions which have been asked by mankind right from the start are going to be answered. So in that sense, it is a very aesthetically relevant question. However, there are also benefits on the ground. Anyone who has used either Wi-Fi or GPS or World Wide Web or touchscreen will attest to the fact that these are things which are almost, unavoidable in today's world. They are things which you can't do without.
Yep.
All of these came up as a product of astrophysics research.
Exactly.
Even the questions which are asked in astrophysics, which led to these technologies were new. So, for example, somebody probably doesn't sit and think that we need Wi-Fi and therefore the Wi-Fi came in that sense. So, there was something which is being asked and new things came out of it, which we have seen almost every day as we speak. With square kilometer array, with these big initiatives, this thing is going to become, this exact offshoot is going to become at least 1,000 to 10,000 times more.
Exactly.
Because of the huge amount of innovation which is needed to analyze these big data sets, which is needed to even obtain these data sets and to clean. So I'll give you an example. When we look at this intensity mapping, one of the biggest challenges, again, in a industrial, in a technology point of view, is that there is a signal. We want to see the hydrogen from cosmic dawn. We want to see that. But this hydrogen signal is in your map, and on top of that signal is 100,000 times bigger signal of unwanted things.
Okay.
What is this unwanted? Unwanted is things in our own galaxy. Our galaxy emits light around the same wavelength. And that sits on top of the signal.
Okay.
Then there are some instrumental effects. Then there are some extraneous sources of light which Now to clean those has proved to be a tougher challenge than initially what was thought.
So you're talking about a filtering kind of thing.
It is something like a filtering or foreground removal, they call it. So foreground is all this matter. Signal is what you have.
Noise removal.
Noise removal, foreground cleaning, foreground avoidance. There's also some innovation in certain parts of your map are less affected by foregrounds. You have to innovate where those are and clean avoid that. So that is one of the things which people do. And so foreground cleaning and foreground avoidance are one of the things which, as we speak, very clever people are using innovative techniques to do. I am sure this will lead to big leaps in technology in the future.
So that's basically like making your life better.
Much better. I'm hoping, I'm sure it will be. So because already we have proof and examples of how it has helped.
Yeah, because the internet came from CERN.
The internet came, the touchscreen, the GPS, we owe it to Einstein's theory. Einstein, I don't think in his wildest dreams, when he wrote these equations, would say it's so important. It's like indispensable, these things.
The Google Maps we are using.
For example, So we use every day the products of astrophysical research, of cosmological research, of theoretical physics.